This is where I left you. I left you with cis and trans discussion, and we were talking about the simple, hopefully, concept of trans being more stable than cis. And then I said, we're getting ready to put it all together. We are. Here. Oh, gosh. Yeah, I know. It looks like a lot, doesn't it? It does. What this is called is a will chart. And this represents all of the reactions that we have discussed in this lecture module as far as alkenes go. Here in the center, what they have done is they have started with a ring with a double bond. So by definition, this is an alkene. And this alkene can undergo a number of different types of reactions in organic chemistry. And all of these we've learned about throughout these series of videos. So the spokes of the bicycle wheel, because we call it a wheel diagram, the spokes are going to be the reagents. And those spokes will point to the products that those reagents will make. So let's do a quick review. A double bond alkene can react with HBr. The double bond breaks, H goes on to one, and bromine goes on to the other. That is what that product represents up there at the very top. Okay? Here, double bond breaks, and we can add water and acid. If that double bond breaks in the presence of those reagents, H adds on to one side, OH adds on to the other. There's the product formation for that one. Double bond breaks, BH3, THF, OH, H2O2, H2O. This was the boration, the anti-Markey mark, right? However, what they want you to do is focus on what gets added on. Double bond breaks, H adds on to one, OH adds on to the other. It's a very symmetrical molecule. They don't want you to think about carbocation rearrangement. They don't want you to think about where it goes. They just want you to focus on what pieces go on to the double bond. That's all that they're after. Next one is alcohol and acid. This is the H+. If you like that better, cross it out. Write H+. Do the same thing up here with water. H+. So if we take acid and react it with an alcohol, the double bond breaks, hydrogen adds on first, and then the O and whatever else is attached to that O gets added on to the molecule. That creates our ether group. This created an alcohol group. That created an alcohol group. This created a halogenated group, because this could be HCr as well, and that could be Cl. This could actually be HI, and that would be I. You get my drift. Next one is the ozone lysis, O3, -78, in the presence here of the dimethyl sulfide. Well, what happened here? We cleave the double bond, and this is a ring structure, so they've just redrawn it. That's all that they've done. But you could go through and you could do what I told you to do, right? The double bond O, elongate this down, come back up, and do the double bond O there. That's perfectly okay with me. I don't care. But this would be a better, cleaner way to write that, because this ring will cleave and it opens up and it spreads apart to give everybody enough room. And this is how it will rearrange itself. So double bond O, here's that double bond O, and double bond O to the bottom, this is that double bond O. If you don't like this though, keep it as a ring structure. I'm going to count it right. Whatever. I'm okay with that. Next is the alkene reaction with the peroxy acid. Double bond breaks, and that oxygen latches on to make an epoxide. What we've learned about recently is a double bond can break in the presence of H2, palladium, and carbon, and that double bond completely disappears. Hydrogen goes on one side, hydrogen goes on the other. They're just leaving them off. We also talked about bromine with DCM. They've left that off, but I'm going to write it on there. Double bond breaks, Br goes on to one, Br goes on to the other. And then finally, they've also included this halogen with some water. We did some of those examples as well. So what you see is the double bond breaks, bromine goes on to one, and OH from the water goes on to the other. Folks, this is a very nice summary of all of the reactions that we have studied so far in alkenes. These are the products that they end up making. You might maybe missed that you learned this much, but you did. And this is the beauty of organic, or maybe the horror of organic, depending on your point of reference. So, we need to use this information, and we need to put it all together into an example. And here's an example. Show how each of the following can be synthesized from an alkene. They have taken all of these reactions and they've just pick and chose, and they've just lumped them all into one master example problem. And they're expecting us to go through and figure out how to make this thing. A couple of other things I want to say about this wheel diagram before we do that example. A couple of other things. I'm going to erase some of these markings on here to clean this back up a little bit. We talked about Markovnikov, right? All of these reactions follow Markovnikov's rule except for one. Do you remember which one it was? That's right. BH3, THF, OH, H2O, H2O2. This is your anti-Marky Mark. That is really what makes this one special. Anti-Marky Mark right there. We also talked about rearrangement. Things rearranging on us. Some of these allowed rearrangement and some did not. As far as the HBr, I'm just going to put a check mark, and that check mark represents rearrangement could happen. All right? H2O with a little bit of acid, rearrangement can happen there as well. BH3THF, rearrangement cannot happen. Alcohol with acid, rearrangement happened here as well. The cleavage of the double bond with the oxygen, no really rearrangement was needed. We didn't even discuss it. The peroxy acid forming this epoxide, no rearrangement was even really discussed there either. Wherever that double bond was, that's where the oxygen went to grab onto those carbons. The H2PD, the breaking of the double bond to the single, no rearrangement we really had to do here either. I mean, these are pretty stationary. Wherever that double bond was, that's where it's going to happen. Br2 and H2O. Well, the reason that this worked is bromine or chlorine, the diatomics, latched onto the double bond, hung out with all three in that threesome, and made up his mind what he wanted to do. Rearrangement did not happen here, and rearrangement did not happen there for that reason. So only a few of these are going to rearrange on us. We just have to keep that in mind, because when we go through and predict these products, that is something that we have to think about. Will it rearrange if this is my answer to the question? Now let's go back and take a look at A. Show how each of the following compounds can be synthesized from an alkene. I'm going to look at A and I'm going to question first, what did they add on? Well, I normally go with the simplest piece. And the simplest looking thing looks to be like this OCH3 group. That's probably what they added on there. Okay, so with that said, what can we do to add on OCH3? Well, this probably came from a CH3OH, right? And that probably came from H+. We needed that as a catalyst in order for this reaction to happen. Wherever this oxygen was attached, that was probably a double bonded carbon at one point in time. Well, if I go left-handed with the double bond or down below with the double bond, it's the same. It's a very symmetrical molecule. There's just 3 of them there. So carbon, double bond, carbon, and CH3. So let me just double check. If I take this alkene and I react it with alcohol and acid, that double bond would break. Hydrogen plays with other hydrogens, Markovnikov's rule, so that goes left. That's where it should go. And then this would open up a carbocation at this site. It can't really move. There's nowhere for it to move to. And the OCH3 would go on to that carbon. And that's exactly what we need. So, folks, we've just answered part A. That's all that we need it to do. So the proper alkene here is going to be 1-propene. Now for B, what did we add on? Well, it looks like we added on 2 BRs, don't it? Right there and right there. Well, how do we do that? Well, we have a Br2 reaction that we could use. Does that require anything else? Yeah, it does. Some DCM if we wanted to be proper. I mean, I guess we could leave it off. They left it off in the wheel diagram, but we could leave it off if you really wanted to be particular with it. But what kind of alkene do I need? Well, this bromine and this bromine, they're neighbors. That's called vicinals, right? Vicinal dibromides. And that is a very good sign that this skeletal structure that we had probably had a double bond right there. Because if that double bond breaks, bromine goes on to the left and bromine goes on to the right. That's how this reaction works. So that's the alkene that we need for B. What's the name of this alkene? 1, 2, 3, 4, 5. So this is a pentene, and that double bond happens at carbon 2. So 2-pentene is going to be our starting alkene that we need for B to work. For C, what did we add on? It looks like we added on this OH group, right? So how do we add on OH groups? There's a couple of different ways. The thing, though, that I have to keep in mind here is that this OH group is added on to the end. That's going to be very hard to do. So, for instance, if this OH group was not there, that means that this carbon had to have the double bond, which means that the double bond would have happened right here. So this would have been my starting alkene, all right? So that's okay. I've been able to determine my alkene at this point. And you might say, oh, OH, well, we'll add water and we'll add acid on. Okay, that's fine. That is a way that you can add OH group onto here. So what would happen, sorry, I'm going to erase that. That's not an O. That's going to be a CH2. So this double bond would break. 2 sites of attachment would open up. And in this case, hydrogen plays with other hydrogens. Well, that would force that hydrogen to go left-handed. So we would actually end up with a CH3 right there. A Markovnikov reaction will not allow that OH group to go onto that outside carbon. We need anti-Markovnikov here, meaning that if we add on hydrogen, it goes in the opposite spot, not where it normally goes to. If it goes to where it normally goes to, we do not get what we're after. So water and H+ is not going to work here. So how do we add on a OH group backward? Well, this is my BH3 THF with OH, H2O, and H2O2. Therefore, in this reaction, my double bond does break. H typically plays with other H's, so it would go to the right-handed carbon. It would go right there. But not in this case. This is anti-Markovnikov. It hates that group of hydrogens that made ton of it. So it goes on to the inner carbon. That leaves this carbon freed up for the OH to attach to. It's the only way we can get that OH group to the end. For D, we do the same thing there. It looks like we're adding on this piece. All right, so I'll draw the ring. There it is. This CH3 is going to be there. And this oxygen is connected to that carbon. I can draw the double bond up or down. I'm just going to draw it down. I mean, no rhyme or reason. That's just how I'm going to do it. And we need to get that OCH3 onto the molecule. Well, where did that come from? That OCH3 probably came from an alcohol. All right, so let's just double check our answer to make sure this makes sense. If I break the double bond, an H and then the OCH3 goes onto that molecule. So breaking the double bond opens up two sites of attachment, one here, one there. And H plays with other H's. All right, so what this means is that the carbon to the top, well, there is no H there. The carbon to the bottom, there's one there. So H goes to that spot and the OCH3 goes to the top. And that's exactly what we need from that reaction. So that is the alkene that we have. That is a 1-methyl cyclohexene. So 1-methyl cyclohexene reacts with methanol in the presence of acid, and that gives us this group, which is basically a 1-methyl and a 1-methoxy cyclohexane. All right, so for E, what do we do here? It looks like we've added a bromine on. How do we add bromine on? Well, if we just want one, it's probably going to be HBr. We don't need to add acid because that's already an acid, right? HBr is an acid. We don't need H+. So I'll draw this structure that has a methyl group on it. That's fine. This bromine is attached to that carbon, which probably means that carbon's got a double bond on it somewhere. So I'll just draw it here. And if this goes forward, H goes on one, Br goes on the other. My double bond breaks. H plays with other H's. Well, this one has one hydrogen. This one doesn't have any. So H goes down below, and then the Br goes up above, and that's where that one ends up going. And then we look at F. F is a ring with O, CH2, CH2, CH3. Okay, so what kind of group should we add on? Well, we can add on this group. That's fine. So I'll end up with, or I'll start with, a ring. That oxygen is attached to this carbon. So we can just draw a double bond there. It's very symmetrical. It doesn't really matter where. And then off of this, I have a CH3, CH2, CH2O, because that's the piece I've added on, and I need to put an H there. Well, what else do I need? Well, if I'm doing an alcohol like that, I probably need a little bit of acid in order for this reaction to work. So I break the double bond. H goes on to one. It doesn't really matter where. They're both the same. And then the O, CH2, CH2, CH3 goes on to the other one. Now, is this the only way that we can make these products? The answer is no. There's a number of different ways that we can make these products. And this is just one round of one answers that I could spit out that kind of makes sense to us at this point, because this is really the only types of reactions that we know. The directions did not give me any kind of criteria to follow. The only thing it said was an alkene. So as long as I stayed with an alkene in the beginning, it didn't really matter what else was on that alkene. I needed a double bond, which is why things like this methyl group was okay. That methyl group right there was okay. I mean, that's why those were allowed, because I'm still starting with an alkene. But folks, this is all of the reactions kind of wrapped up into one problem. I also want you to keep in mind that there's a reaction here that's missing. This shows you the importance of that reaction, and what is missing here. Can you pick it out? It's the mercury. They didn't even write that onto the spokes of this wheel. So that shows you the importance that they think the mercury plays in today's organic environment. They'll mention it. We talk about it. The mercury methods are another way of adding OH or another way of adding this OR group onto these molecules. If I go back to this example problem, here we added an OH, here we added an OR, here we added an OR group. We could have maybe brought Mercury into this discussion a little bit. Not with this one, because this goes backward. But with this one we could have, and with that one we could have. And instead of choosing H plus and alcohol, or H plus and alcohol here, we could have easily chose the mercury routes that go there. That would have been an alkoxy mercuration. So that would have been another possible choice that we could have done in order to make these products with. There's more than one answer there. But they've lifted off the spokes of the wheel. So, again, that shows you the mentality. We don't like you to work with mercury. We mention it, but we don't want you to work with it so much that we don't even put it onto the diagram in the textbook that talks about it. Can you believe that? All right. So, folks, this is it. This is the world of alkene reactions. And this is your first taste of organic reactions as we know it for now. So what's going to happen is that in the next lecture module, we are going to combine what we've been doing into one lecture. And this is going to be a different functional group, and we're going to learn how to name that functional group, but we're also going to learn the reactions of that functional group at once. So I've thrown you into the lake. I've been teaching you how to swim, and now you need to prove that you can't drown. That's what this next lecture module is going to be, because we're going to be tackling both of these concepts at once. All right, so reactions of alkenes. There you go. You've got a number of different reactions under your belt at this point. Keep in mind carbocation rearrangement. Keep in mind Makovnikov and anti-Makovnikov reactions. What allows the rearrangement, what doesn't. And a few mechanisms that go along with this discussion as well. So folks, out of all the lecture modules so far, I would say this one might be one of the more difficult ones, and you're okay. If you feel this, if you feel that this is a little more complicated than some of the others, it is. I'm not going to disagree with you, but don't lose hope, right? That's the number one problem that people have in organic. They think that they can't do it, and they struggle, and they struggle, and they struggle, and then one day, I guarantee you, one day, you're going to wake up and you're going to go, this makes sense. Why didn't it make sense like 2 weeks ago? It's just like someone turned on a light bulb. Snap of your fingers. It's like a whole different world begins to open up and you get it. And that will happen to you too. You just have to stick with it. You just have to keep practicing. You have to keep writing down these structures, and you will get there if you're not already there. Some of you are, and some of you will be. So good luck with this lecture module. Good luck with these online assignments. Good luck on this material with the upcoming test. If you have questions, you know desperately how to get a hold of me. I'll be here for you. I'll be waiting. Come and cry on my shoulder. I did it. You can too.